have a dot product. And that they have this, you know, this inner product. Like, I
you only care about the
wave
properties.
functions here. So what happens in like the Dirac notation, you're simply taking these very analytic solutions that you recognize as having all the properties of a vector space, a Hilbert space, right? And just saying, look, I don't even need to write down these wave functions ultimately, right? All I need to know is that that was an n and that's an n plus 1. The integral is equal to 0.
Well, it's n and any non-equal to n.
Sorry, n and m, yeah, thank you. N and m for n not equal to m. Yeah.
But it's also nice to go through all that machinery and know it and understand it. So
Yeah, so you
you're not
keep...
just
Yeah,
shooting
it's useless
dark
if you don't
and
actually-
That's right.
with these-
Like you couldn't, if someone just said, here, just do it, you would lose all the satisfaction of, you know, using this technique, all right? And then you do have to start off by actually building these functions to see that they form an infinite basis set and they have all those properties. So once you understand all that stuff, you're ready to just kind of go to that.
Are those, and right behind you there, are those size of ends right there, or they're just ends?
These are ends.
These are just ends.
And this should be an h bar. What's that?
No, let's say it says.
Omega h bar over 4 2n plus 1. Okay? So this is the expectation of potential for the nth what? Stationary state. Not the total wave function, the stationary state. Alright?
Expectation value for the.
Well, we just used the stationary states. We didn't use that full-blown, general wave function. We just calculated the expectation value of the stationary state.
And that comes up to the end.
Say that, and that
That's
comes
the end.
That's it. Yeah. Okay? Great. I'm very happy to do all that. It's fun. It's nice when you can do it. It certainly doesn't come for free, but when you can do it, it's nice. All right, now we're going to get into some even better stuff, all right? In a way, this is a little bit of a side note. We're going to come back to that whole idea of, building this linear combination of stationary states. Well, I guess it's all the same. In essence, guys, what we've been doing is a Fourier series. We found these nice basis sets, like sines and cosines, and then we built a function in terms of this basis set, right? Now, when we built it in terms of this basis set, the basis set was, you ready? I'm going to use this word I've used before, denumerably infinite. When we solved for Schrodinger's equation, time independent, we got stationary solutions that are integer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that when we built our total solutions, we had a summation over those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Integers go beyond 10 though.
Yeah, they do. Last we checked.
That's
they
what
do.
denumerably infinite.
Yeah, we checked. Yeah. All right? So it's a lot like discrete probability. Remember when we calculated averages and discrete probabilities? That what we had to do is we had to do the summation of p sub I times whatever the value was. Okay. We then went from discrete probabilities to continuous probabilities. Remember we did this? Mm-hmm. And when we went to continuous probabilities and we had to compute the average, what happened to our summation? Okay, it became, what I say, continuously infinite. All right? As opposed, what I mean, so here are my words, I'm not sure if they're standard. Denumerably infinite means 1, 2, 3, 4, 5, 6, 7. Continuously infinite means there's a continuum. There's
fractional.
It's differential, yeah. There's an infinity between 1 and 2. It's continuously infinite. So when we moved from discrete probabilities, we had the infinite summation over numbers. And then when we went to continuous probabilities, it's right in the book, first couple pages. All right? We went from discrete summation over numbers to an integral. All right? And when we integrated, we weren't integrating over a probability per se. We integrated over probability density. All right? So here's the scoop. When we're making a summation over an infinite basis set that is denumerably infinite, that's called a Fourier series. That's a Fourier series. What we're now going to do is we're going to solve for the free particle. In the free particle stationary states, are they stationary? Yes, they're stationary. All right, the free particle stationary are not denumerably infinite. What do you think they are? Continuously infinite. So the only thing in our whole machinery is going to be when we go to create this total wave function, and we make it summation over CNs times those bases. What do you think this is going to look like? This is going to be, so our basis set now is not denumerably infinite, it's continuously infinite. So we're going to have our psi general is going to equal, not a summation, an integral. Okay? So an integral. And now, are we going to have CNs, which are probabilities, or are we going to have what Matt just said? We're going to have a probability density. So probability density times that wave, times our basis set over whatever space we're in. All right, and that's called the Fourier integral. Everybody see the difference between the Fourier series and the Fourier integral?
It sounds undelightful.
Well, hopefully it's an enlightening discussion that we're having. All right? So that's what we're going to do. So the whole thing is that we're going to do the free particle, and we're going to find the free particle basis set is not, well, we're going to find it has lots of problems, actually. One of the problems is that it's not normalizable. All right, so when you hear not normalizable, what should you worry about? You should worry about a lot of things, right? If it's not normalizable, can you add up the probabilities to equal 1?
No.
If you can't add up probabilities to equal 1, are you talking about a physical thing? No. Okay, so the solutions, are they very physical?
No.
They can't be.
So if you have a
That's
particle
really
in a
example
vacuum,
2, problem 2.2.
What's that?
You're talking about the stuff in problem 2.2.
I forget the number.
if you have a particle in a vacuum,
Yeah.
that would be a free particle.
Yeah, with no potential.
Yeah.
Yeah.
So are you saying that a particle like that, because the probability densities do what you just said, that
So here's the
you
deal.
couldn't locate it?
We're going to have an unphysical basis set. So it means that our particles cannot be represented by a single one of these. But they still form a complete basis set, right? It may not be Hilbert, right? But it still forms a complete basis set because it's from separation of variables. So it turns out that physical objects can be built as a combination of these basis sets, of these unphysical basis sets. So our physical property is built as an integral, continuous summation of these unphysical basis sets. And those things are called wave packets. So just to summarize, wave packets are going to be the physical objects, or the physical solutions that represent real particles. And wave packets are built out of these basis sets that are unphysical.
So I guess I'm not understanding, like, I know Fourier series you take it by taking subsequent derivatives, and then each one of those derivatives is you know, one of those, what was that word you used, denumerative, because you're taking each integral is a new integer number, you know, like that's what the way it works out. But how do you do the Fourier integral? You know, like, I just don't.
How do you do Fourier's trick for Fourier integral?
Yeah.
Oh, just too clever. We'll get you. Yeah, go ahead. But it's the same idea.
The parallel that you had was that when we have that probability of summations, it's
Yeah.
kind of chunky,
Yeah,
and we
When you
take
take
the
the
integral
integral.
form
Yeah.
over probability density.
yeah.
And what is that paralleling? What would be the probability parallel in that analogy?
So let's go through, let's do it, all right, and see if you can see it. I'll set it up, I'll put these ideas in your head, and I want to draw the connections, and let's see if we can pull it all together.
Okay.
All right.
I thought you said that, I just missed it, that's all.
I may have, but I think maybe I'm going to do it better by solving the problem. Okay, so next problem, our free particle. Free particle Schrödinger. Okay, so here we go. Here's x, and then here's the potential, and it equals 0. Equals 0 everywhere. Okay? So it's not even hard yet. It's not even interesting yet. All right? What's the first step we do when we solve quantum mechanics problems, guys? We drew a picture. We drew the potential energy.
Write down the Schrödinger.
So write down Schrödinger. So here we go. H psi equals IH partial of psi with respect to t. What's next?
Separation of variables.
Separation of variables. What are we going to separate out first? The time. What is that time going to come out to be? G of t is going to equal e to the minus I E n over h bar t. Everybody agree? What are we left with? Okay, so you guys are starting to get it. All right? Are we doing anything different?
The text has the stationary states with the time piece in there. They mentioned it twice. They mentioned it earlier in chapter 4, but they keep mentioning, oh, blah, 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 stationary states, and there's the time piece in there.
And it's true, the total stationary state is the solution here. But what we showed is and I'll just sketch this out briefly, is that when we calculate expectation values, we've got to go psi star psi, something to that effect.
Right.
So when we do throw in the time-dependent part, it becomes e to the plus I t over h bar times psi.
They mentioned talking about that too. They mentioned language behind that. All right.
Times psi. And so what happens?
Right.
These things go away.
Right. Okay. And they mentioned something about that.
Okay. Yeah. All right. So Matt is correct. The total wave function is the total stationary state solution. Okay. Okay. So what's our next step after we do the separation of variables and pull out a time? What are we left with?
Time-independent Schrödinger.
Time-independent Schrödinger's equation. So h times psi of x. And anticipating we don't know here, but maybe psi n equals en psi n of x, right? Okay, so then what do we do? So we've got to solve the time-independent equation. So what do we have to do? Let's call this is the unperturbed Hamiltonian, so I'll put it H0. It's the unperturbed Hamiltonian for the free particle. We're not talking about the unperturbed Hamiltonian for the harmonic oscillator or the infinite well now, right? This is just the unperturbed Hamiltonian for this particular problem. So what do I need?
So just a summation of potential and
I need kinetic and potential energy, so I need EK plus EP. I'll put a little operator times psi n of x equals En psi n of x. All right, let's put in what they are. What is the kinetic energy?
P squared over 2m.
P squared over 2m, but now we'll jump right to the answer. Equals
H bar squared.
minus h bar squared over 2m partial squared with respect to x squared.
we can use total derivatives.
And what's that?
We can use total derivatives because it's
Oh,
Yeah,
yeah, I
partial.
like that, Elmore. Very good. Let's use total derivatives because it's only a function of one variable. Yeah, cool. What's the potential?
0.
0 times psi n of x equals En times psi n of x. All right. All right. So let's goof around with this. All right, and I'll write this as psi n of x prime. All right, plus, let's see what we've got. We've got 2m times En over h bar squared times psi n of x.
Equals 0.
All right, and let's get this into the form that we always like. What am I going to call this?
We're going to call it K.
If it was a function